Take a look at it just generically before we get into the homework problems. If we're just looking at kind of the most basics, let's look at how do we sketch these things. So hopefully at this point, after doing all the synthetic division, we can take things in standard form, so something like x cubed plus 5x squared plus yada 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 yada, and be able to put it in a linear factor. So I'm going to just start it off in linear factored form. So we'll have something like x plus 4 squared, x plus 1, x minus 2 cubed, and then something like x minus 5 to the 4th. So this is going to be probably more complicated, so to speak, than I would ever give you, but this allows us to talk about all the behaviors and stuff that we're going to look at as a whole. So this is going to be our function to start off. It's already in factored form. So what are my x-intercepts? My x-intercepts are x equals -4, -1, +2, and +5. Okay? And those x-intercepts have different multiplicities, right? So first thing I want you to identify is what is the degree of this function? So normally when it's in standard form, we look at whatever that highest exponent is, but now it's in fact the linear factored form. So what is the degree of this function? Talk to your neighbors real quick. Okay, what's the degree of this function? Okay, I hear 10. Anything else? 9, 10. Okay, how do we come up with 10? There's 2 x's there. There's 1 there, so there's a total of 3. 3 more puts us at 6. 4 more puts us at 10. So this has a degree of 10. Okay, what's going to help us with that is we want to know, is it even or odd? 10 is obviously even. So what's its end behavior? It's up and up, right? So just like squared or to the 4th power or any of those others, right? Anytime it's an even degree, it's going to have some sort of an up and an up. It's going to start over there, and it's going to end over there, going up towards our positive infinities. Okay, we have our x-intercepts, which we've identified at 1, 2, 3, 4, and 1, and 1, 2, 3, 4, 5, and 2. Okay, so we have our x-intercepts. The next thing we're going to take a look at is the multiplicities of each 0. So the multiplicities of each 0 will either be even or odd, and they will also behave similar to what we're thinking. So if I'm looking at -4, the multiplicity is 2. So what do you think it's going to behave like when it gets to that point? Is it going to cut straight through, or is it going to bounce kind of like a parabola? It's going to bounce like a parabola. So just like we would expect something that was x squared to behave like a parabola, this will behave like a parabola. So around here, it's going to bounce. Okay? At -1, what do you think it's going to do?
Cut straight through.
Cut straight through, because it looks like a linear function. It's going to behave like a linear function. So it's going to cut straight through. Okay? How about at +2? It's going to, Chris? Good. It's going to behave kind of like a cubic, right? It's going to get that little swiggle effect to it. So when it comes back up to it, it's going to go through, but it's going to have kind of that cubic behavior to it, because it's multiplicity of 3. Okay? How about at 5? Go through or bounce? It's going to bounce again. Good. To the 4th degree, though, it builds a slightly larger trough, if you've ever seen like the 4th degree functions. So this still bounces, and when you do the sketches, it doesn't have to be perfect, but it ends up being a little bit of a wider trough. But the key piece of this is it's going to bounce. Okay? So now all we have to do is really kind of connect our dots. The last piece that we normally look for, which in my example is a terrible one to look at, is the y-intercept. Our y-intercept is going to be something ginormous, because if we plug in 0 for x, you'd end up with 4 squared times 1 times negative 2 cubed times negative 5 to the 4th, which that's really, really big numbers. We're going to be somewhere in the multiple thousands. So let's pretend that's way down here at something huge, really big. Yeah, really big. Yeah. Anyway, so it's going to come down here through the y-intercept at some point. It's going to come back up. Okay. And then it's going to go somewhere else. I don't know exactly where it's going to go to, but eventually it's going to come back down. This is going to take off for forever because that was our end behavior. This will at some point turn back around, and this will take off for forever. So there's roughly a sketch of what that graph's going to look like. Okay? Where the key pieces we're worried about are those x-intercepts, the end behaviors, and for the problems tonight, you'll have easier y-intercepts to find, and so you'll be able to look at those. So this is what we're going to be able to do. You're going to take something, you're going to factor it all the way out. You'll have it in linear factored forms. You'll have some multiplicity, and we'll be able to go from there. So first one we're going to look at tonight. They'll give you the graph, and we'll just ask you some stuff about it. So state whether the degree of the function is even or odd. So for number 24, let's take a look at this one. Is that going to be even or odd? Odd, good. Anytime you have an up and a down, it's going to be odd. If it was flip-flop, it's still odd, but it would be negative as well. It gets flipped. So this would have, for number 24, this would be odd. Degree. Not necessarily an odd function, but it has an odd degree. Use the graph to name the zeros. So our zeros in this case would be able to look at. So our x-intercepts are going to be negative 3, negative 1, and positive 2. And then they're going to say state whether the multiplicity is either even or odd. So the multiplicity here, is this going to be even or odd? Odd, because it goes right through. Good. So anytime it crosses the x-axis, we're going to have that odd multiplicity. Anytime it bounces, we'll have even. So this would be an odd multiplicity. Okay, for negative 1, that's going to be, because it bounces, we'll have even. Good. And then for 2, we'll have even. Okay, good. And then the next piece that's going to be asked is going to be state the minimum possible degree that this function could be. So if we think about it minimally, okay, anytime it cuts straight through, the smallest multiplicity it could be is 1. Anytime it bounces, the smallest multiplicity it could be is 2. So this would be 1, 2, 3, 4, 5. So the smallest degree this could be is a 5th degree polynomial. Okay, which fits our first guess that it's going to be an odd degree. So 5th would match. Okay? So anytime it's even, assume that the smallest it could be is 2. And then anytime it's odd, assume the smallest it could be is 1. And then estimate the domain and range, assume all these zeros are real. So my domain in this piece, what kind of x's can I put into there? All real numbers. Good. Okay. I can put anything I want into this function. It goes on for forever left and right. Okay. How about the domain, or how about our range? What's our y values? All real numbers, because we have one up, we have one down tail. Anytime you have an even degree function, so something like your homework, number 23 here, because it's up and up, there is going to be a limited range. So you want to look at, oh, this is all real numbers from y greater than or equal to negative 9. So you want to take all those values above that lowest point. Okay, so that's what we're going to look at, is just identifying and talking about some of the stuff on those first few problems. Next one we're going to look at is it's going to start just like that first example we saw, where it'll be in factored form for us. We're going to state the degree of each function, the end behavior, and then the y-intercept of this graph. So number 30 as our example here. The degree of this function, 1, 2, 3, 4. So we have a fourth degree function. There's 2 there, 1 here, 1 here. So the fourth degree function tells us it's even, so our end behavior is up and up. What would tell me if it was down and down? Or is down and down an even degreed function?
If it was negative.
Good, if it was negative. So if both tails go the same direction, either up, up, or down, down, it's going to be an even, but the negative will tell you if it gets reflected across that x-axis. So right now this is positive, 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 so it's going to be a positive up, up, even degree function. So then the last piece is what's the y-intercept? Y-intercept is found by plugging in 0 for x. So when 0 goes in here, we'll have 2 squared. Gives us 4. Times negative 4. Times positive 1. So we'll end up with negative 16 for our y-intercept. Negative 16. So technically this is the coordinate point 0, comma, negative 16. Okay. And we do not need to graph these. Okay. If we needed to, we'd be able to basically just plot these y-intercepts. So you'd be able to end up at 1, 2, 1, 2, 3, 4, and negative 1. We have up, up with a bounce. So we're going to go here and back through down to negative 16 and back up. Okay, so you'd be able to get a rough sketch that looks something like that. The last stuff we're going to do today is take all of this and piece it together from the very beginning, and we'll give you a regular function in standard notation. Make you find the x-intercepts in linear factored form, and then have you guys graph it. So something like number 58. We'll end up with, so anytime we're back to the regular, how do we go and put it in the linear factored form? Using our synthetic division, goodly. So we're going to go back to that original thing. So I've got 1, negative 13. Just kidding. How many x squareds do I have? 0. Don't forget our placeholders. So 1, 0, negative 13, 12. Okay, always like to start with 1. We can quickly check, is 1 going to work? Yes, if we add that across, that will turn into a 0. So let's go ahead and use synthetic division on it. 1, 1, 1, 1, negative 12, negative 12, 0. Okay, cool, that one worked. We're left with x squared plus x minus 12. What's going to multiply to negative 12 but add to a positive 1? Positive 4, negative 3, so we'll end up with positive 4, negative 3, and then the factor we pulled out earlier, which is this x minus 1. So now we have it in linear factored form. To help us with graphing these, I think it's good for you to know the degree. What's our degree of this function? 3. Good. So what's my end behavior? It's going to start in the down, end with the up. So we're going to start down, we'll end with the up. Okay, if we're looking at it on the coordinate grid. Okay. And then we'll just look at the x-intercepts from here. So our rough sketch will have us at x equals negative 4, 1, 2, 3, 4. X equals positive 1, x equals positive 3. All of these particular ones have a multiplicity of 1, so they're just going to cut straight through. And do we know where our y-intercept is? These ones are the easier ones. Try to overthink it. What's my y-intercept for this function? 12. Good. If I plug in 0 for x, all that's going to disappear. So we're left with 12. So in theory, somewhere up here at positive 0, 12, we should have a y-intercept. Okay, and we're going to see if that makes sense as we fit it. So our end behavior said it's going to start from the down. It's going to cut straight through. Okay, it's going to go. Oh. It's going to go through our y-intercept. Come back through that x-intercept. Turn around at some point. Back through that x-intercept and continue off for forever. So our end behavior matches. Our y-intercept fits, and it goes through all of our x-intercepts with multiplicity 1. There's our graph. Cool, huh? All right, so that's what we're doing today.